Right, so welcome to the last talk of this semester's talk, this year's talk. And today's speaker will be introduced by Thomas Beatty.
Okay, so I met Paul, I think we met 5 years ago in Warwick, right?
Yeah, I think so.
At the conference. But more germane to Paul's career, even though I think that was a big event for him, was that Paul did his undergrad at Berkeley, did his PhD at BU under Phil Muirhead, and then went and joined UC Riverside as a postdoc, and is now an NSF postdoc with a visiting appointment at Santa Cruz. Paul has worked on actually a bunch of stuff. I was looking this up, Paul. I did not realize all the stuff you worked on. So you started on solar system and Cassini observations?
That's right.
Yep. Solar system and Cassini observations of Saturn. Atmospheric refraction and exoplanet transmission spectra, and I think has really made a name for himself doing the detection through transits and RV observations of long period giant planets and characterizing them, which is what he'll talk to us about today.
Yeah. All right. Well, thank you so much for the introduction. I'm happy to be here. Thank you to everyone in the room. It's really nice to be in a room with people. So thank you for being here. And of course, everybody online, thank you for calling in as well. I'll try to split my attention between the camera and then everybody in the room for the talk. Yeah, I'm Paul. I am primarily based out of UC Riverside and Stephen Kane's group. And I think I saw Stephen on the line. So hi, Stephen. But I also have a visiting appointment at UC Santa Cruz, and that's where I live. Today, we're going to be talking about giant exoplanets, and specifically the ones that are cool, not just really cool, but actually cooler in temperature, and what we can learn from them. So because, let's see, there we go. When it comes to giant exoplanets, the story usually starts here in the solar system with Jupiter or Saturn. So I like to kick off my talks with this imagery of Jupiter coming from the Juno spacecraft, which I think a lot of us have probably seen it. If you haven't, you should definitely keep a close eye on the pictures coming out of Juno, because it's just really phenomenal. And it's amazing to think of all the giant exoplanets we've discovered, and that there may be some sort of, this is what they may look like, or maybe they look entirely different. But it's just really wondrous to think all the different possibilities that are out there. But with Jupiter and Saturn, they act as really wonderful ground truths for what we want to know about giant exoplanets. We can go to Jupiter and Saturn, we can study them. And that's a really, really key part of the puzzle of giant planets as a class of astrophysical object. And really, we want to know them as a class of astrophysical object, all of the various ways they're similar and different from each other, to have a full understanding of giant planets. But that's just one piece of the puzzle that is the giant planet class. That's Jupiter and Saturn. They have, exquisite spatial temporal detail, ground truths, but they're not a statistical sample. They're only 2 data points. And what we're finding is that even those 2 data points are surprisingly, remarkably different from each other. So this is the benefit of exoplanets. This is why the rest of the puzzle generally involves larger numbers of exoplanets. In the top left corner here, the hot Jupiters offer a very unique piece of the puzzle. With a hot Jupiter, you can measure the mass, the radius, the atmosphere, if you're able to get transmission or emission spectroscopy. But there's a little bit of a hiccup there, and it's with the radius measurement. For most hot Jupiters, their radii tend to be inflated by an anomaly that's still an active area of investigation. So if you wanted to try to use that radius along with the mass to say something about the interior properties of this planet, you're going to be pretty model dependent on what you're going to say, because we're still trying to figure out what this radius inflation thing is. So hot Jupiters may not be the best case uses to study the in-depth interior composition of giant planets, especially cooler planets like Jupiter or Saturn. So there are other giant planets to help us with this. Another piece of the puzzle is imaging and RV surveys. And that's what I show here in the bottom left. And I think my little GIF has stopped rotating there. But with imaging and RV surveys, you can measure the mass of the planet really well. And in the case of imaged planets, you can oftentimes get the atmosphere too with a direct spectrum. And that is indeed going to be the future of giant planet analysis, I'd say. You can determine if there are other objects in the system sometimes. That gives you the system architecture, puts a little bit more of a full picture on the story. But alas, you are left with no radius. So there's still that problem of what are we going to do for the radius? And in the case of imaging surveys, at least for right now, they're biased to younger planets that are still self-illuminous. So when it comes to mature, cool planets, think like an actual Jupiter analog, we're not quite there yet. We will be soon. And the decadal was pointing to that in a lot of ways, but we're not there right now. So this leaves this bottom right piece of the puzzle where transit surveys for cool or colder exoplanets can fit in. Just like the hot Jupiters, we can measure the mass, we can measure the radius, we can measure the orbit, and eventually the atmosphere with a little patience and a little bit of luck. We don't have the problem that we're just stuck with young self-luminous planets. They can actually be mature planets like Jupiter or Saturn. Empirically, we know that radius inflation isn't so much a problem if you get that planet pushed farther away from its host star, so that we can trust the radius measurement as a way to then look into the interior of the giant planet. But the big problem here is the low transit probability. As you get more than 10 days away in orbital period or so, that transit probability just really plummets, just falls off. And so therein lies the challenge. But that's the challenge I'll be speaking about today. This is just a quick outline of what I'll be talking about. The main question I'm going to focus on is, how do giant planets accrete their heavy elements? Turns out that's a really important piece of the puzzle of how they form, where they form, when they form, and what kind of migration they undergo. So that's the central theme of what I'll be working on or speaking about today. I approached that question with the Gotham survey, which I'll define a little later. And I'll present 2 case studies of planets that are in the Gotham survey. I wish I could talk about all of them, but I wouldn't have time to get through them. The 2 I will talk about is Kepler 1704b, or the highly eccentric one, to help you remember from the talk. And then there's also TOI 2180b, which is TESS's longest period planet, with a huge asterisk there that I'll mention. And the paper describing that one was actually accepted to AJ like an hour ago. So I'm really happy to be presenting to you newly accepted results there. After I talk about the Gotham survey, I'll explain how we're looking for trends in the giant planet mass metallicity correlation, and I'll describe what that is and how that then answers the question in bullet point number 1. And then I'll finish by talking about atmospheres, and I'll tell a tale of 3 metallicities. So this question: how do giant planets accrete their heavy elements? Well, for many of the giant exoplanets that we've found so far, we think that they form via core accretion theory. And that happens roughly loosely in 3 phases here. And that's what this diagram describes. In the first phase, we primarily have heavy elements that are building up and forming to some sort of planetary embryo or core here. And what's being shown on this plot is just time on the X and mass on the Y. So once this core, through various methods that I'll talk about in just a second, once that core gets to be a couple Earth masses or so, it can then start getting a little bit of hydrogen and helium. That's what we're seeing in phase 2. So we see that some hydrogen helium gas is beginning to accrete. That's driving the mass increase for this part of the formation. And this is where we start to get to the point of metals being on the same mass of hydrogen and helium. This is where we can start forming Neptunes or mini Neptune-like planets. And then it's not until right at the end where we cross a critical threshold and we can start a runaway accretion of gas. And that's where we get into our big gas giants like Jupiter. This is the general theory here. And an important aspect of this that is very hotly debated in giant planet formation theory is this very first part, right at the beginning. How are these heavy metals coming together to form what is the seed of these giant planets? Are they planetesimals, which is something that could be on like kilometer scale sizes that are accreting together? Or perhaps they're pebbles, which are something more on like centimeter scale sizes that are accreting together. Or perhaps it's some mix of both, as the complicated case is probably going to be the accurate one. But each of these different options, planetesimals or pebbles, has some ups and downs. We know that planetesimals exist in these systems and exist in the solar system as well, but sometimes it can take too long for them to accrete, to get enough mass to actually lead to runaway gas accretion before the gas disk dissipates. Well, enter the theory of pebble accretion, and pebble accretion can be just hyper efficient to the point where some population synthesis models that use pebble accretion actually overpredict the number of giant planets. We know that that's not the case because we have a decent idea about the population of giant planets. So
I'm in there, the word efficient there, you have to be very careful how you use it. Pebble accretion is, in terms of how the mass is processed, it's an incredibly inefficient process.
Sure.
It's very fast.
Sure, yes, that is a good clarification, yes. It can lead to the production of giant planets though, very efficiently, I'll say, yes. So getting this mystery figured out of what's the dominating method, planetesimals, pebbles, and then how that propagates down the line through core accretion theory through these other two phases to eventually what we can actually observe either through bulk composition or in the envelopes of these giant planets, that's all really important. And that's sort of the goal that the Gotham survey is heading towards. Something we do know about the metals in the envelopes of giant planets is that they're enriched relative to their host stars. So this plot just shows a handful of volatile elements and noble gases. This is from the solar system, and the y-axis is just the planetary to protosolar ratio of these. And you'll notice that all the data points are sitting above the line here at 1. So Jupiter, Saturn, Uranus, and Neptune their envelopes are all enriched in metals relative to the sun. Jupiter by a factor of a few, Saturn by a factor of 10 or so, Uranus, Neptune by more than that, although it's still fairly uncertain. This is my plug to let's get a flagship mission sent to Uranus and Neptune sometime in the next decade or so. That would be fantastic. So we know that there is metal enrichment, and that in some way ties back to how these planets formed. And in exoplanets, we have somewhat of a similar story to be told, not exactly the same. I won't draw exact parallels, but as far as bulk metallicity measurements go, we have found that there is bulk metallicity enrichments relative to stellar for giant exoplanets. So I'm showing a plot here that is the ratio of metals from the planet to the star on the Y, and on the X, it's just planet mass. And this is the giant planet mass metallicity correlation I'll be referring to throughout the talk. And this comes from a paper by Daniel Thorngren and collaborators back in 2016. Each of these giant exoplanets is thought to be cool enough that radius inflation didn't affect the measurement of bulk metallicity. And bulk metallicity is measured using giant planet cooling curves and the measured mass, radius, and age of the system. So you evolve your planet down the cooling curve, and then you can tweak the heavy element mass of the planet to then recover the radius. And that then gives you the bulk metallicity of the planet. So it's important that you can trust your radius measurement when inferring bulk metallicity from these cooling models. Everything I'm showing here is above 10 to the 0, which is 1. So the point here is that giant planets, at least in a bulk sense, seem to be enriched as well, just like the solar system. But there's a lot more to be taken from this plot, and that's what I'll be covering as we go through the talk still. Specifically, that formation models like pebble accretion and planetesimal accretion make different predictions for what the slope is of this correlation. Now, what I'm showing here, the Thorngren et al. Results, that slope is consistent with planetesimal accretion, at least in the late stages of formation. So I was always curious are there different distributions of giant planets in this figure? Or if we could add more data to this figure, could we actually see different trends coming out? A little bit of foreshadowing for what's to come. But we can't view it too simply. We have to keep in mind that giant planets don't form in isolation. The full story includes the architecture of the system, are there companions, whether they're planetary or stellar. We have to consider the migration, because many of the giant planets in that plot I showed previously likely didn't form right where we see them today. So there's migration, there's the eccentricity of the planet, what that might tell us about scattering events or maybe mergers, and all of that complicated business goes into the full story that we're looking at. One way to approach this, though, is to get a larger sample of giant planets with diverse orbital periods or orbital properties, not just right up next to the host star, but as far out as we can, with measured radii, masses, and orbits, and eventually atmospheres. That would be fantastic. This is where the Gotham survey comes in. So the Gotham survey is the Giant Outer Transiting Exoplanet Mass Survey, Gotham for short. And it's really just kind of breaking it down. It's a survey that's meant to take planets that were discovered as transiting planets, either by Kepler or TESS, and then to follow them up to measure their mass. That's the main goal, or I'd say that's the first level goal of the Gotham survey. In the case of the Kepler planets, they're generally around fainter stars, and so you need a little bit of a bigger telescope to follow them up with radial velocity, Doppler spectroscopy. So for the Kepler planets, I typically use the Keck telescope in order to measure the mass. TESS, on the other hand, has this bright star advantage. It's looking all around the sky, focusing on the brighter stars. So we don't need as much glass in order to follow those planets up. And so for TESS, I've generally been using the automated planet finder telescope that's at Lick Observatory. And the APF is fully Q scheduled, so that's also very, very convenient. But But I want to break down the GOTAM survey a little more, and we can do that by analyzing the acronym. So at its core, GOTAM is a giant exoplanet mass survey. These are long period transiting planets. They're about the size of Jupiter, roughly. And many of them are or can be validated. I'll say validated means some statistical threshold that these are likely planetary based on an analysis of all the false positives that could explain that particular event. But even with that validation, there's still a very high false positive probability. So I tend not to believe validated giant planets until you can actually get a mass measurement. And there are several brown dwarfs hiding in the GOTAM survey that are in the NASA exoplanet confirmed exoplanet table too. So it's always good to have a little bit of skepticism with the validated giant planet. So first and foremost, with this mass survey, we're going to confirm that this is actually a planet. After that, we're going to be able to refine the orbital eccentricity to have an idea of the formation history or migration of the giant planet. And then that also identifies companions. Is there a substellar companion somewhere that might be driving some form of migration? Are there a bunch of interior planets that might have stayed on circular orbits? How did those planets form if you had a giant planet outside of them, maybe eating up all of the metals? Just getting the full picture. Now, giant exoplanet mass surveys have had great success previously in exoplanets. They've looked at planets that are close in on the order of a tenth of an AU, out to moderate distances, and even the longest running mass surveys are now starting to get out to the orbits of Jupiter and Saturn. So this is a highly successful technique to use for characterizing exoplanets. But if we add in transiting, now it gets a little harder. I'm focusing on non-inflated planets so we can know the bulk metallicity and eventually get an atmospheric measurement, and also make a safe assumption about the interior composition. And for transiting exoplanet mass surveys, we've really been stuck at the inner 2/10 of an AU because of that transit probability, the selection bias of the transit method. But we're trying to get out from that. And so we're pushing out to intermediate distances, I will say. So we're talking AU scale, maybe a couple AU. This is 100 days orbital period out to 1,000 days orbital period. We are not quite getting out to where Jupiter and Saturn are. The probability is just too vanishingly low out there to get really any transiting exoplanets. I would love that to be the case. But we're really working on these giant exoplanets that are stepping stones in between hot Jupiters and the Jupiter, all with the idea of do outer giant planets accrete heavy elements more differently than close-in ones. Okay, so now we're going to talk about data and a few of the individual systems. I'm an observational astronomer at heart, and so that's what I like to talk about the most. This is a really, really busy slide, so don't be too overwhelmed by it. It's just a subset of the RV curves of all of the planets in the GOTAM survey. For x-axis where you see large numbers, that's time, and where you see small numbers, that's just phase folded. It's not particularly important that you take in each one of these. Just notice the highlighted boxes that identify the orbital periods. These are all transiting planets, and these are all planets that have been subject to 3 going on 4, if not longer, years of RV follow-up. So we have hundreds and hundreds of days, and this one over here in the top left is almost 1,000 days, and this isn't even all of them. What I'm going to have time to talk about today are just going to be these 2 in the upper left corner. And these are the 2 that are just about the farthest along, although almost all of these are nearing publication. So let's start with the first one, Kepler 1704b, which is one of the most recent Kepler planets to be confirmed. What Kepler saw is what's up here in the top right, 2 transits, one in quarter 2, one in quarter 13. These transits are only 6 hours long. That's relatively short. So having 2 6-hour transits separated by almost 1,000 days immediately throws up a flag of eccentricity. Could also be impact parameter, but eccentricity in that case. And sort of an unfortunate aside here, right in the middle of these 2 transits that were separated by 1,000 days, right in the middle there's a data gap. And the data gap was, I think, a day or 2 days long. So you could easily have lost a 3rd transit in that data gap. So when I started observing this, I operated under the idea that the orbital period was probably going to be 495 days. It's just more likely given the fact that this transits. That was false. That was indeed not the case. To my very happy surprise, this is a planet with an almost 1,000-day orbital period. These are the Keck-HIRES RVs folded on that particular orbital period. And this intensely cuspy model that we have indicates that the eccentricity is on the order of 0.92. with a very small error bar. So it is a highly eccentric giant planet. I display the orbit here. KOI 375 is Kepler 1704b. It's the same name. And this orbit, which we're almost looking straight down, right down the periaps axis of, it comes within 0.2 AU of its host star at periaps, and then on the other side at apoaps, it's about 4 AU away. So it's for whatever superlatives are worth, I don't think there is a transiting exoplanet with a known period that has a periaps greater than 4 AU. So I love showing it with respect to the solar system because it gets out into Jupiter's territory and it goes within Mercury's territory. And it's also fun to see it relative to HD 80606b, which is perhaps the community's favorite eccentric transiting exoplanet, and indeed the target of a James Webb campaign coming up. So there's a lot of fun things to do here. I mentioned previously that with RVs, you get a better idea of the system architecture for your systems. And so for Kepler 1704, we didn't detect any outer companions. We had AO imaging and also our 10-year RV baseline, a very modest sample of RVs, but it did span 10 years and it was pretty flat. So through some analyses, we were able to rule out, large stars and some substellar objects, but there are still pockets of parameter space where a companion could exist. We can't rule out all of it. So I think this would be a perfect case for a dynamical study to see where there's areas of stability that would allow a companion that could perhaps cause this kind of high eccentricity orbit. So that's future work to be done. So we're left sort of with the idea that maybe this was formed via planet-planet scattering. And the fate of the other planets or planets that cause the scattering are unknown. One other fun thing to mention about this is atmospheric characterization. Now, just calculating the scale height and comparing that as the change in transit depth, it's not perhaps a great target for transmission spectroscopy. However, this thing is under 200 Kelvin out at apastron, and then it zooms into periapstron and it increases by 700 Kelvin, at least for an equilibrium temperature metric. So what happens to the atmosphere when that happens? If you've ever wanted to take Jupiter and drag it up next to the sun just to see how its atmosphere would respond, this is the system for you. You can conduct that experiment every 3 years with this system. So what I'm showing in this plot is just the flux ratio of the planet as a function of orbital phase. And for almost the entire orbital phase, nothing is happening because the planet is moving slowly out at apoaps. But over a course of about 2 weeks, we get a really nice peak. And depending on what assumptions you make about whether the atmosphere is well mixed or whether the heat stays on a hot day side, you can get an increase in flux of the order of 50 parts per million up to 150 parts per million. So more substantial modeling is called for, but these numbers aren't vanishingly small. Even for a 13th magnitude Kepler star, this is in James Webb territory. So there's some exciting work to be done to see how hazes form or are destroyed, how the atmosphere responds. And something I think would be particularly fun to see, this single increase and decrease is probably oversimplified. You could imagine that this giant planet is probably rotating. And it's far enough away from the host star that it's probably not pseudosynchronized because the tides aren't strong enough to circularize the orbit or likely aren't strong enough to to get the rotation to be locked in with the star. So if it's rotating like Jupiter every 9 or 10 hours, what we would see instead of this single peak is we might see a ringing feature. And the ringing feature would be a way for us to directly measure the rotation period of the planet. And that would be a really, really exciting measurement to have. Especially for a planet that is not tidally locked. And anybody who does climate modeling knows how important planetary rotation is. And so this would be a big win for this system. All right, let's talk about another case study. This was the Kepler case study. Now let's talk about a TESS case study. And the baseline of TESS is much shorter than that of Kepler. So when a long period planet transits, you're typically left with single transit events. You don't get 2 transits, you don't get a bunch of them, you just are stuck with 1. And so it's a bit harder to do the follow-up. But it can be done. This is TOI 2180b. In the top right, you see the single transit that TESS observed. It's a nice bright star. That's one of the parameters that I'm going to highlight here. V is 9.2. So that's almost 4 magnitudes brighter than Kepler 1704, just for comparison. And the data look really clean because it's a nice bright star. And that transit that TESS discovered is 24 hours long. So if you just, it's a subgiant star. So the star is a little bit bigger, so that accounts for at least some of the reason why that transit is longer. But having something that long immediately screams, oh, this could be a long period planet. There was also a bunch of other test sectors observing this, and there was no other transit event to be seen. So that's also a good sign if we're searching for long period planets. This event was discovered by citizen scientists, I will say. I work with a group of citizen scientists that immediately look through the test data, the full frame images, once they're public. The citizen scientists work with their own software that they've developed. And when they find a really neat event like this, they send it to the TESS Single Transit Planet Candidate Working Group, of which I'm a member, and we can get it on the telescope that night. And so that's how it worked for this one. And I show the RV data for this planet in the bottom panel here. These RVs are from the APF in blue, and then a little bit filled in from Keck-HIRES. Given how bright it is, we don't need Keck-HIRES, but this was a period of time when Lick Observatory was shut down owing to nearby wildfires. So we were able to cover some of the gap there. So we had the citizen science discovery here. We immediately started following it up. And when we got to after this turnaround, we said, okay, we think we're heading towards transit again. And what we wanted to do was try to guess or calculate, could we determine when the next transit is going to occur and can we catch it? And by catching that transit, we would really, really refine the orbital period uncertainty, which at this time was still on the order of days. And that's necessary to do because you can't ever write an HST or a James Webb proposal and saying, well, we want to observe this transit and it's going to happen on the 14th plus or minus 10 days. That's out immediately. It's too uncertain. You have to recover a second transit in order to know the ephemeris and then to be able to observe it again in the future. So that's what we tried to do. And I'll just highlight again that the citizen science discovery allowed us to do this. It allowed us to get the observations and attempt to observe the very next transit that came around. This planet wasn't identified as a TESS object of interest until right around here, right before that next transit. And that's no fault of the TESS team. This is not the goal of what the TESS team is trying to find. This is very low priority work, but it's high priority work for giant planet studies. And so it was excellent to have their contribution. So we did conduct an observing campaign. The summary of it is here. There were observers on 3 continents. We had 14 telescopes, including more citizen scientists who contributed to this. That ended up producing 55 data sets over the course of 11 days. That's what I'm showing here on the left. And over 20,000 individual exposures of TOI 2180. So it was a huge campaign. I contributed myself. I headed out to Joshua Tree National Park. I use these 2 telescopes. These are EV scopes, which is made by a company called Unistellar that you can use for events like this, but citizen scientists all over the world have them too. Funny, I'll take a brief aside to tell a funny story. These EV scopes have an onboard computer, and the computer holds 16 gigabytes of data, which I took pretty much over the course of the evening for each of them. But if anybody's ever been out to any national park, especially Joshua Tree, there's no wireless signal. And I was staying at this tiny little shack that also had hardly any Wi-Fi signal. And before I could do the next night's observation, I needed to upload the data off of these telescopes. And I was sitting on 32 gigabytes of data and absolutely no signal. It was also August in Southeast California, so it was like 110 degrees. So I drove into town and I thought, where could I go to upload this data? And so immediately I think like Starbucks. But Starbucks is closed because it was the middle of a pandemic. You can't go inside. And I can't sit outside because it's so hot that, after 20 minutes, you get heat stroke. So I thought McDonald's with the same deal. After frantically searching, it turns out that Walmart was the place to go to upload these data. If you ever need Wi-Fi, the upload speeds at Walmart are incredibly fast for whatever reason. So each day I would download the data from the telescope to my tablet. I had to do them one at a time, and I'd spend 2 hours walking around Walmart uploading the data. So I got to know that Walmart very well. The best Wi-Fi speeds are at the pharmacy. Anyway, this is the data that was produced by that.
On that, Walmart lets you sleep in their parking lots too.
They do.
Wow.
They do. Yeah.
Years.
Yeah.
Connected to the Wi-Fi, I'm sure.
Exactly. Yeah. So here's the data that we ended up with. I'm showing that each one of these is just flux as a function of time. They're all stacked on each other with time increasing as you go down. They all have the same time offset subtracted from them. I show the transit model up here in the top left, not because I think that's when the transit occurred. In fact, it didn't occur then. But just to give you a perspective of, it's a pretty shallow transit. It's like 0.5%. And we're using ground-based telescopes that are 1 meter or less. So this is going to be tough. Even though it's bright, it's going to be tough. So if you imagine dragging that transit model across all of these possible light curves, what you'll get in the end of that is no convincing transit detection. So we have a non-detection of transit, unfortunately. But on the flip side of that, there are many times in which we are confident that we did not see ingress or egress. For instance, this the blue data points right up here. We're quite confident that we did not see ingress or egress at that time. So that rules out part of the transit times, which then rule out part of the orbital period posteriors. And that's exactly what I'm showing here in this figure. The nice Gaussian normal shape are the posteriors on orbital period that come from modeling the RVs and the single transit from TESS. When we then incorporate all of the times we were able to rule out using the ground-based data, we can actually chop out a couple chunks, including this most likely chunk right here. And that leaves us with a bit of a refined orbital period. And that actually then allows us to make a prediction that TESS is going to recover a transit of this planet itself in February of next year. I forget which sector it's going to be, but in February, it will transit again, and TESS should, unless for some reason TESS doesn't observe where it's planning to observe, TESS should recover this planet. And that allows a nice validation, hopefully, of this method.
February, like 2 months from now.
Yes, February is in a couple months from now. Yeah, so I'm excitedly awaiting that. So it observes it in February, and it'll be down in March, and so we should know by then. Yeah. So just kind of summarizing this campaign, we ended up taking 4.4 days worth of exposure time of all of the telescopes across the entire campaign, and that led to us ruling out about 3.8 days of posterior parameter space for the orbital period. So these campaigns don't happen very often, but it'd be useful to have some kind of metric of how well you did, or should we have even done this? Was it efficient? And so I treat this as somewhat of an 80% efficiency rate of almost every second that we spent on target was ruling out a second of orbital period of parameter space. So before I get back to the bigger picture part of the talk, I'll just mention there's a bunch of other interesting systems. I have some backup slides on some of these if you're interested. There's 3 more TESS single transit sub-Saturn sized planets actually with orbital periods between 85 days and 350 days. And these are really interesting because they seem to have a variety of metallicities, bulk metallicities, despite being about the same size and similar host stars. So there's an interesting investigation to be done with different metallicities of sub-Saturn planets there. We have a low density Saturn planet that has TTVs that fall in what's called the so-called exomoon corridor, which was a recent exomoon theory paper put out by David Kipping collaborators. And so there's going to be 2 papers coming out on this next year, but we may have ourselves with a new exomoon candidate or exomoon candidate host. And the RVs are going to be measuring the mass of the host planet, which can then be propagated through the model to predict the mass of the moon, which right now could be a sub-Earth mass moon, we suspect. Can't say too much more about that, but look out for some exciting papers coming next year. And then I don't want to leave the brown dwarfs out of this. They find their way into the Gotham survey. And there's one, a pretty typical brown dwarf that's in the optimistic habitable zone of an F star, which is really cool. And lastly, there's a Jupiter mass planet that's a single transit from TESS that is about to undergo 6 days of straight observations with NEOSAT, which is a Canadian space telescope. Those 6 days of straight observation are happening next week. And we're hoping to recover the second transit of that one at that time. So plenty of exciting results to come from this survey. But for now, let's get back to how giant planets accrete their heavy elements. This is the question I'm really trying to focus on. And let's bring it back to this figure, which is the giant planet mass metallicity correlation. Again, the metallicity of the planet relative to the star on the y-axis, and then the planet mass on the x-axis. This was the work of Thorngren et al., indicating that the slope indicates that it is consistent with planetesimal accretion. But if we dig into the sample of planets from that plot a little bit more, what we find is they're all fairly short period, relatively short period. The median period is 12.5 days, And this histogram just shows the orbital periods of the Thorngren planets and the orbital periods of the Gotham survey planets. A similar plot exists if you plot them in terms of insolation or stellar flux. And in the same case, the Thorngren planets kind of push up against the boundary of where we think radius inflation for giant planets kicks in. And then the Gotham survey fills in everything at lower irradiation, longer orbital period. Only a handful of the current ones in that sample have orbital periods greater than 100 days. So there's not a ton of diversity in that 2016 paper as far as orbital period goes. There's room to do better, and that's something the Gotham survey can do. It'll add at least 10 more planets with longer orbital periods. Yeah.
I was wondering about the histogram. Are the histograms for the three samples overplotted, or are they stacked?
Oh, they are stacked.
Okay.
Stacked, yeah, thank you, yeah. So the one thing I wanted to explore was when we add these new Gotham planets into this figure, where are they gonna lie? Are they just gonna blend in perfectly? Are they gonna reveal a different slope? Or are they gonna reveal the exact same slope? Really, either answer is interesting. So the very first attempt at doing this, I'm working on an entire paper that focuses on this with more planets, but the very first order attempt that we put into the paper publishing TOI 2180 separated long and short periods at 100 days, which is an arbitrary fiducial number. The part of the investigation is going to determine where that separation should actually be, and if orbital period is the proper parameter to actually do the separating. But just separating at 100 days, we show all of the same Thorngren et al. Planets with circles, and the blue ones are short period, the red ones are long period, and then we include a handful of the Gotham targets with triangles, and then TOI 2180 that I spoke about here as a square. Just fitting lines to these, essentially power laws to these data points, we do see a difference in slope for the short and long period planets at a 2.6 sigma confidence. So not particularly compelling, but maybe the hint of something, probably worth exploring in a little more detail. The slope of the shorter period planets is fully consistent with that from the Thorngren et al. Work that I showed a few slides back, and it is consistent with population synthesis models that say that metals are accreted through planetesimal accretion. As the slope becomes more steep for these longer period planets, it becomes more consistent with pebble accretion. So perhaps this is early evidence that there is a difference in, or the preferred pathways of accretion are different based on where these planets end up. So maybe migration factors in to how the planets accrete their elements and how their bulk metallicity ends up for these planets. All work still to be explored a little bit more, as 2.6 sigma is still a bit tentative, but it's indicating that there might be a difference, which I think is pretty exciting. Okay, in the last segment of the talk, I want to look forward, focus on what's next after the bulk metallicities, once the Gotham survey finishes measuring all the masses it wants to do. And atmospheres is almost always the way that goes. So I'll start off by just stating that transmission spectrum features may be observable for some of the Gotham planets, despite the low equilibrium temperatures, despite the fact that they probably have clouds, all of them probably have clouds, and despite the fact that refraction can become a bit pesky when you get to longer orbital periods. I argue this point by showing the transmission spectrum of Saturn as if Saturn were a transiting exoplanet. This is back from a paper I did as a graduate student. I do the citation there. It used data from the Cassini mission, and Cassini had an instrument that was called the Visual and Infrared Mapping Spectrometer, VIMS. And VIMS had sensitivity between 1 and 5 microns, amazingly similar to NIRSpec and NIRIS on James Webb. And what you could do is you could essentially invert observations of solar occultations at Saturn to turn it into the exoplanet transit geometry, and then calculate the transmission spectrum, transit depth as a function of wavelength for Saturn. And that's what we see here. We see features of methane that are on the order of 50 parts per million or so over here. And then this whopping feature, the one that's 90, approaching 100 parts per million, is from ethane and other larger hydrocarbons that are present in the atmosphere of Saturn as a result of the ongoing photolysis in the atmosphere and disequilibrium chemistry. So if we just think of Saturn, even though Saturn's quite cold, if we could get a cool exoplanet that's not too massive, so the gravity isn't so high on these planets, we may be able to see the atmosphere that sits above the clouds. That's what we'd be seeing for Saturn. So there's reason to explore these cooler giant planet atmospheres. And there's theory motivating the observations too. And that's what I'm showing on this plot. This is a figure from a Fortney et al. Paper recently that talked about identifying vertical mixing in the atmospheres of cool giant planets. So for this figure, it's equilibrium temperature on the X and then just volume mixing ratio of a handful of species in the atmosphere on the Y, just focused on the dashed lines at first. Those are run from models that assume equilibrium chemistry. So as we're going down in equilibrium temperature, this orange dashed line, which represents CO, it falls off around 800 Kelvin. And at that same time, CH4 starts picking up around 800 Kelvin. That's equilibrium chemistry. That's what we expect. Cooler atmospheres are going to be methane dominated, and hotter atmospheres are going to be CO dominated. But this paper found that if you include vertical mixing that can actually dredge up material from deeper, warmer parts of the atmosphere, that transition between CO and CH4 gets pushed to lower equilibrium temperatures. And there's some sort of relation between how much mixing you have and where that relation ends up, or where that trade-off from CO and CH4 ends up. And you can see these temperatures, 400 Kelvin, 600 Kelvin, 200. We need to get down to cool temperatures to try to validate, or at least to try to test these models and to test the importance of vertical mixing in giant exoplanets, which is challenging to do, but is very likely ongoing, at least in some way, because we know from Jupiter and Saturn that it is. We know from brown dwarfs as well that vertical mixing plays a role in what we see in their visible atmospheres. So the Gotham survey is a way to do that as well. Part of the problem, or maybe this is actually an exciting aspect, is that James Webb is not going to do this in ERS, GTO, or Cycle 1. The planets that we need in order to test that theory of vertical mixing, none of them, they would essentially fall into this gray hatched region here of higher mass planets, but cooler temperatures, temperature being on the y-axis. And of all the planets James Webb is going to look at least that are published and I'm able to see, none of them fall in there, with the exception of this one little planet here. This is WD 1856, which is a wonderful and exciting, but totally specialty case. So there's so much room to do this in the next round of James Webb. And the last thing I'll mention is just the tale of three metallicities. Once we've been able to actually measure atmospheric metallicities for even just a small subset of these cool giant planets, we will have three metallicities then that tell as much of the full story as we can hope for. The first is the metallicity of the stellar atmosphere, just from stellar spectroscopy. The second is the atmospheric metallicity that we would measure from transmission or emission spectroscopy. And then the third is the planetary bulk metallicity that we'd have along the way because we will have measured the mass, the radius, and the age, and then included giant planet cooling models. So these are the three metallicities. And one possible explanation for how these might relate to each other, a simple expectation perhaps, would be that the planetary metallicities will both be greater than the stellar metallicity. Giant planets will be enriched relative to the star. That's not big news. It's probably going to be the case. But then also possibly that the bulk metallicity will be enriched relative to the atmospheric metallicity, because perhaps some of these metals will be sequestered into a deep core. This kind of gives us an idea of how heavy elements are perhaps distributed inside giant planets, and how all of that points back to the host star. It's just a simple expectation. It'd be worth testing. In the solar system, we know that the case is very much more complicated than that. We have really phenomenal stringent gravity data from Juno that gives us an idea of what the distribution of material is inside Jupiter, for instance. And what papers that have done, efforts have done to try to understand metallicity gradients inside of giant planets, they've found that for Jupiter, there may be multiple compositional gradients. And that's what this fairly involved plot shows. Some sort of diluted core and a couple different composition changes all the way up to the surface of Jupiter. And even metallicity inversions as well, which seems very strange. Now, this level of detail won't be possible for a giant exoplanet, but there'll be context. Even having those two metallicity measurements, bulk and atmosphere, bulk and envelope, will help us with a few larger numbers, help us get an idea of where Jupiter and Saturn fit in terms of other giant exoplanets as a class of object. So that brings me back to my outline slide, which I'll treat as my summary slide. How do giant exoplanets accrete their heavy elements? Well, maybe not a full answer, but possibly they accrete them differently based on their orbital period. That's an answer that needs to be run down a little bit more with a few more giant exoplanets in the Gotham survey, of which I talked about two, the eccentric one and TESS's longest period planet. To explain that asterisk, that superlative doesn't have a ton of meaning because there are going to be more long period exoplanets, some of which are in the Gotham survey, some of which are not, that are on their way out. So TESS is slowly but surely going to fill in that area parameter space between 100 days of orbital period out to 1,000 days, slowly but surely. And then TOI 2180 will just be another one of those long period planets. I identified possible trends in the giant planet mass metallicity correlation that maybe start to answer question number one. And then looking forward, we see how James Webb is going to allow us to get atmospheric metallicities that sort of finish out the entire puzzle. So I think with that, I'd like to acknowledge my collaborators and also acknowledge the use of the telescopes on Mauna Kea, which is very much a privilege to be able to use, and I'm grateful for that access. Subset of my collaborators are here as well. Also, specifically want to point out the TESS Keck survey, the CPS group, and my two citizen science groups, the Exoplanet Watch Network, the Unistellar Citizen Science Network, and everybody in the TFOP groups that find these planets in TESS data. So with that, got them, and thank you.
Are there any questions?
So quick one on so the eccentric system, was it 1204? So
1704, yeah.
Yeah, so amazing, amazing one. So you commented that you didn't expect spin to be synchronized, obviously, with the total orbital period, but don't you expect the spin to be pseudo-synchronized, meaning that the spin rate matches the instantaneous orbital angular speed as it goes by? I thought that was the story for 80606b. And
so yeah, I'm not entirely sure if it will be pseudo-synchronized. You can calculate that pseudo-synchronous timescale. I think it's a couple days is the length of the rotation in the case of 1704b. The difference between 80606 and 1704 is that the tides are much weaker for 1704 because it only comes into about 0.2 AU. 80606b comes in close enough that we think it's actually in the process of being circularized. 1704b is not in the process of being circularized. And I forgot to mention in the title, the name that we call that planet is a failed hot Jupiter, which is a name I think that comes from Becky Dawson's papers back in the early 2010s, which is funny because it seems like everybody's trying to become a hot Jupiter and this one just happened to fail. Whatever caused this high eccentricity migration, it didn't quite bring it in close enough that the tides would be strong enough to cause it to circularize. So for that reason, we're not sure that the tides are strong enough to actually cause pseudosynchronous rotation.
Yeah, I didn't get that it was that far away.
Yeah, I hadn't mentioned, that was, thank you for the question. Yeah.
Are there any questions from the online audience? If you have a question, please raise your hand.
And Tom?
Otherwise, I will ask a question. So can you show the graph again where you show the planet mass versus metallicity, which are two models?
Sure. This one?
Yeah. So the normalization factor on the y-axis is that solar luminosity, or is this the not luminosity, metallicity, or is this the metallicity of the planet with respect to its host star?
It is the second one, is with respect to its own host star.
Okay.
Yeah. So having each of them above unity means that they're all together enriched relative to their stars.
I had two questions.
Okay.
So one, do you think, is there going to be a point where Gaia starts really producing where you'll be able to supplement your RV data with Gaia astrometric measurements for these systems?
Yeah, I've attempted to do that. Let's see. Do I have that figure for 1704 or for TOI? Let me go back to TOI 2180 real quick. Sorry for the hopping through. This would be the perfect case for an inclusion of Gaia astrometry. Because something I didn't mention was in the residuals to the planet fit, you see the nice Keplerian planet fit there. There was a very nice high confidence detection of curvature in the RV fit as well. So there's something else in this system. And it isn't the host star activity or something like that. In a case like this, a nice bright star, you would essentially want to use Gaia parallax and mixed in with Hipparcos as well, like the Hipparcos Gaia catalog of accelerations. The only problem is, for reasons I don't know, this was not observed by Hipparcos. It's not part of the survey. So we can't use that, because if we were able to do that, there have been some recent papers that combine the astrometry and RVs and essentially make wonderful constraints of exterior objects, masses and orbits. And this would have been a perfect test case for that, but we couldn't.
Right.
With many of the other ones, we are able to do that, and that will be part of the analysis. Yeah. But with TOI 2180b, we were just left with sort of like a long posterior that sat in mass and separation space for what the external object was. And in this case, it could be a planet, it could be a star, it kind of just depends.
But you wouldn't, so would you get astrometric detections of the planets themselves?
Oh, I see. I know that Gaia is expected to discover a good handful of giant planets. Some of these, the Kepler ones, probably not. I'd be skeptical about the Kepler detections, but for perhaps this one, maybe. I haven't actually gone in to see if Gaia has detected this one or some of the others. Like I said, Kepler ones, I would say doubtfully, but the TESS ones, perhaps.
So we got a question in our chat from Howard, and he asked on the same plot again of metallicity versus mass, if you have considered different splits on the data,
Right.
maybe some physical motivated splitting.
Yeah, I have. That's going to be the aspect of the final Gotham paper, is to go through and determine, is orbital period actually the parameter we should be doing the splitting on? Is there any meaning to the 100-day separation? Probably not. I will say it was fiducial. And so to answer your question, I have not attempted doing that with other splits. That is worthy of its own study as a whole. And yes, picking something that would be actually physically motivated and perhaps working in insulation instead of orbital period, I think is going to be revealing.
Can I do one more? Quick one? You should go. Mine's a softball.
Okay. Yeah, mine maybe gets the main idea, right? Obviously, so one of your goals, obviously always a good goal, is to try and constrain planet formation theory. Obviously, it's also very complicated to do, but I guess the idea, let me see if I got it right, is that you expect sort of a more or less constant core mass for pebble accretion because you open a gap that stops the flow of pebbles.
Yes.
That's okay, yeah. So I see a couple of issues there. Is that one, the pebbles are going to pile up, and then what's going to happen to them, right? You've got this incredibly large pebble flux. Obviously, there's people working on that to pile them up, and then fine, they would maybe turn into planetesimals before they get dumped on, but it's still just a variation on the theme. And then also the idea of are the masses actually synced up? I mean, this Thorngren result is remarkable because it suggests that the amount of heavy elements in most giant planets is not around 10, 20, or even 30, but there's plenty that are 100 or 200. I mean, not many, but there's certainly
There are some
ranging up there. And the point being that, right, Jupiter is on the low end of things in its mass range, which, even though our estimate of the amount of metals in Jupiter has been steadily going up over time, still everything else is even higher than that. So this seems like this is sort of actually well above the masses people say for actually, opening the gap and cutting off the pebble supply. So that even if the trend is right, it's not clear the numbers match up.
Sure, I see. Yeah. I'll also mention that in the case of 2180 and 1704, both of them are on the order of 100 Earth masses of heavy elements, based on in bulk metallicity as well. So they're on the high end as well.
Yeah, no, this is the thing. So it's like, so you think, oh, theorists explain. No, theorists are generally surprised that there are so many metals in these giant planets, right? We talk about it all the time. And just as an advertisement to everyone here, Daniel Thorngren obviously has this very important result, is coming to our group meeting on Thursday.
Oh, cool.
Be discussing some of his latest results. So we'll be safe here. not on our mailing list, it'll also go out to the TAP mailing list. And if you're not on either of those.
Maybe you could send it to Origin Seminar list and
Sure.
or a subset of us.
Sure. Yeah.
Cool. Yeah, tell them I say hello.
Yeah, we won't be here in person. It'll be a Zoom thing, but yes, we can still say hi.